If you've been wondering in these videos why I always approach from this side of the board and why I always seem to be looking off to my right, it's because that's where my computer is and I have to verify that it started recording before I start talking to make sure I don't waste 20 minutes talking in an empty room and then not having it recorded. So in chapters 8 and 9 of the textbook, the next section we're going to study is reactions that both produce alcohols and ethers and reactions of alcohols and ethers with other reagents. So both the synthesis and the reactions of alcohols and ethers, but let's start with the synthesis of alcohols and ethers. So from what other functional groups can we prepare alcohols and ethers? And we've already seen examples where you can produce alcohols or ethers from alkyl halides by substitution reactions. So this section should be review because you are already familiar with substitution reactions with alkyl halides as the substrate. So if we were to start, for example, with 1-bromopentane and we were to wish to convert that into 1-pentanol, we could do that reaction readily with hydroxide as our nucleophile, as either the sodium or the potassium salt. And this reaction can occur in almost any solvent, or it can occur in the absence of solvent by just adding sodium hydroxide to an excess of 1-bromopentane, which is a liquid. Often, you'll run this kind of reaction in a two-phase mixture, so you'll have aqueous sodium hydroxide, and then you'll dissolve the halogenated alkane in a solvent in which it's soluble, like hexanes, which has a nice boiling point of 69 degrees C, so it's easily removed later, and we can quench the excess hydroxide ion with a sodium bicarbonate solution. And you will do a reaction very similar to this in the lab, where you take a mixture of, where you take 1-butanol, and you react it with a mixture of concentrated HCl and HBr, and do the reverse reaction. So we're working with aqueous sodium hydroxide, hexane to dissolve the non-polar bromopentane, and an SN2 reaction is favorable in this case, right? If we have a tertiary alkyl halide, like 1-iodo, 1-methyl, cyclopentane, we can convert that to the corresponding tertiary alcohol, 1-methyl cyclopentanol, simply by heating it in the presence of water. And doing a sulfolysis reaction, hydrolysis in this case because it's water, it's the solvent. And this goes by an SN1 pathway rather than the SN2 pathway that we had with the primary substrate and sodium hydroxide. It's possible to make ethers by exactly the same type of reaction. So if instead of reacting 1-bromopentane with sodium hydroxide, we had reacted that with sodium methoxide in methanol. Recall methanol being the most common solvent for methoxide ion because the sodium methoxide is often made in situ by adding sodium to methanol. We would expect to get the corresponding primary ether, methyl 1-pentyl ether, or 1-methoxypentane. Depending on whether you use IUPAC nomenclature or common names. This reaction, the reaction of an alkoxide ion with an alkyl halide, is known as the Williamson ether synthesis. And the Williamson ether synthesis is likely to be successful in producing an ether product rather than an elimination reaction if you're working with a primary substrate and a primary or a methyl substrate and a primary or a methyl alkoxide. If there's branching at either position, either the alpha carbon of the alkyl halide or in the alkoxide ion, then E2 elimination is likely to take over and the Williamson ether synthesis is much less effective. Any alkoxide can react with a methyl substrate by the Williamson ether synthesis because in the absence of a beta hydrogen, the only possible pathway is the SN2 pathway. So the Williamson ether synthesis is a useful way to make alkoxide or to make ethers from alkyl halides as long as both the nucleophile, the alkoxide ion, and the substrate, the alkyl halide, are either primary or methyl. But they both have to be primary or methyl for it to be effective. Simply by switching the solvent from water to ethanol and heating it up, we will have a different solvolysis reaction where the nucleophile is now ethanol instead of water. And we can make tertiary ethers, in this case, the ethyl ether rather than the methyl ether because we're working with ethanol solvent. So the SN1 solvolysis pathway works for tertiary alkyl halides using either water to form alcohols or an alcohol to form ethers, and the SN2 pathway with a strongly nucleophilic base like hydroxide or an alkoxide on a primary substrate with no beta branching is going to give us a primary alcohol with hydroxide and a primary ether with an alkoxide ion. The challenge comes when we're working with a secondary alkyl halide and we would like to make an alcohol or an ether from the secondary alkyl halide. Because with that branching, we increase the stability of the carbocation and thus the likelihood that instead of having an SN2 reaction, we have an SN1 reaction. And that's okay if we don't have any stereochemistry to maintain, but it's no good if we do have stereochemistry that we wish to maintain. And that branching is going to increase the likelihood that if we're working with hydroxide or an alkoxide, we'll get elimination as a major pathway that's competing. Sorry about that. Supposed to be an alkyl halide. So we're working in this case with S, 2-iodo, pentane. And what we'd like is we'd like to maintain our like to make So we'd like to not have a racemic mixture. We'd like to have this reaction be stereospecific. Which means we want it to undergo an SN2 reaction, not an SN1 reaction. If we were satisfied with the racemic mixture, we could apply exactly the same conditions we applied in the tertiary substrate. We could simply heat this up in the presence of water, and we would get a racemic mixture of R and S 2-pentanol. If we're going to get a stereospecific reaction and force this to go by an SF2 pathway, we can't use hydroxide. Because if we use sodium hydroxide, the likely pathway especially if it's aqueous sodium hydroxide that we're using, the likely pathway that we're going to get out of this is elimination. And since the base is unhindered, we would get the state-side product, and we would get the more stable trans product. So we need some way of avoiding the elimination, which we would get if we use the sodium hydroxide, and not allowing the SN1 pathway, which is what we would get if we simply heated it up with water. To make an alcohol, the obvious nucleophiles are hydroxide ion or water. If this oxygen can't have come from either water or hydroxide ion, we need to find a source of oxygen that is not basic enough to cause an elimination pathway, but still nucleophilic enough to displace the iodide in a concerted step rather than waiting for the iodide to leave. So we need kind of to hide the fact that it's hydroxide. It needs to now look like hydroxide. We need an oxygen nucleophile that is less basic than hydroxide, but more nucleophilic than water. And can be converted into hydroxide in the subsequent step. So we're going to use a masked hydroxide ion, effectively. It won't look like hydroxide, so the substrate won't know that it's going to become hydroxide, and it won't react with it in an elimination pathway by removal of a beta hydrogen. But then once it's reacted, that initial material will be converted to the OH group. So what kind of reaction, or what kind of nucleophile can we use where there's an oxygen nucleophile that's less basic than hydroxide, perhaps because it's resonance stabilized, but still a better nucleophile than water? We'd like it to be negatively charged. The obvious choice is to use the acetate ion. We can reduce the basicity by resonance stabilizing that anion, which softens it and makes it less likely to take a proton off and do an elimination reaction. Acetate ion is a weak enough base that usually doesn't do elimination as the major pathway, but it's a good nucleophile, and especially if we use a polar aprotic solvent, we can enhance the nucleophilicity. And let's increase the rate to get it to outcompete the SN1 reaction, which could occur if we use a protic solvent. So the reaction conditions for the first step, which will actually not make the alcohol, it will make the acetate, are to use in a polar protic solvent like DMF or DMSO. So if we write that reaction out, what we're looking at with our S2-iodo pentane, reacting that with potassium acetate, in a polar protic solvent. Recall that DMF is dimethyl formamide. And it looks like this. Two methyl groups on nitrogen provide steric hindrance around the partially positive carbonyl carbon and prevent it from solvating the acetate ion. And remember, OAC is acetate, where the AC refers to that carbon-oxygen double bond with the CH3 group. So it's an excellent SN2 reaction. It will be concerted with inversion of configuration. The hydrogen will be pushed up. And we will make the R isomer of 2-pentyl acetate. So we've succeeded in forcing the reaction to go by an SN2 pathway, maintaining our stereochemical integrity and resulting in a stereospecific inversion. Of configuration. From the S stereocenter to the R stereocenter. Now what we need to do is cleave the carbon-oxygen bond between the carbonyl carbon and the oxygen, which has taken the place of the iodide, without affecting the carbon-oxygen bond between this sp3 carbon and the oxygen that we just put in there with the acetate. The conditions for that are potassium hydroxide in water, and this reaction is referred to as saponification because it's the same reaction that allows you to make soap from animal fat, for example. If you take lard and treat it with lye, which is a hydroxide solution, you can make a soap out of it, where saponification comes from. The mechanism for this is not the nucleophilic alkyl substitution. The sp3 hybridized carbon, the chiral center, is not involved in this mechanism at all. This is a nucleophilic acyl substitution reaction occurring at the carbonyl carbon. And it's the first example of a nucleophilic acyl substitution that we've seen. The potassium is a spectator ion, so the hydroxide ion is the important part. And what that hydroxide ion is going to do is interact and break the pi bond. The pi bond in this case is weaker than a sigma bond. The pi bond is where the LUMO is. The LUMO in this case is actually a pi star orbital. So that pair of electrons that used to be in the pi bond will be pushed out onto the oxygen, and you will convert this carbon. And you'll notice that the chiral center is unaffected. And intermediate is tetrahedral at the former carbonyl carbon. This reaction is reversible. There's nothing to prevent that pair of electrons from coming back and kicking out the hydroxide ion. So step one is the nucleophilic attack of hydroxide ion on the carbonyl carbon to break the pi bond. Step two is for this pair of electrons on the anionic oxygen to come in and reform the pi bond, but instead of kicking out the OH group, it's going to kick out the OR group. That's also a reversible reaction. It's the loss of the alkoxide ion. And it's very unfavorable. Alkoxide ions are not good leaving groups. In fact, in a nucleophilic alkyl substitution reaction, the alkoxide ion would not be an allowed leaving group, and you would have to conclude that there would be no reaction. So how do we convince the alkoxide ion, despite the fact that it's a strong base and a terrible leaving group, how do we convince it to leave anyway in step two? And the way we do that is we promise it something. We say, if you leave now, we will give you a very acidic hydrogen in step three. This hydrogen has a pKa of about 5. The pKa of the hydrogen in the product is about 15. So step 3 is an irreversible. Where the alkoxide ion removes the carboxylic acid hydrogen to form the alcohol. And generate the acetate ion. And you should be able to calculate the equilibrium constant for that reaction, knowing the pKa of a carboxylic acid, which is about 5, and the pKa of an alcohol, which is about 15. So that's a 10 order of magnitude difference. And if you remember how to do that calculation, you should conclude that the equilibrium constant for this reaction is approximately 1 times 10 to the 10th. And anything that is 10 to the third or greater than 10 to the third, we say goes to completion and is thus irreversible. So in this case, the irreversible proton transfer, the incredibly favorable acid-base reaction in step 3, is what drives the equilibrium forward, even though steps 1 and step 2 are equilibria, and this is an unstable intermediate that's not very favorable to form. Once you form it, it reacts instantly, and that drives the reaction by Le Chatelier's principle. So overall, it's 4 mechanistic steps and 2 reactions. The first reaction is just a single concerted step where the acetate ion kicks the iodide out in SN2 reaction with 1 transition state. And then the saponification reaction is a 3-step nucleophilic acyl substitution where the hydroxide ion attacks the carbonyl carbon to break the pi bond. The tetrahedral intermediate reforms the pi bond with the loss of the alkoxide ion, and then an irreversible proton transfer, transferring the hydrogen from the carboxylic acid, acetic acid, to the alcohol, or to the alkoxide to make the alcohol, drives that reaction.